data given. So whatever data is given to us in this example, we'll write over here. A DC generator supplies load current of 80 ampere at 400 volt. So it is very simple to understand. Load current which is given to us, IL is equal to 80 ampere. The next is this 80 ampere is at 400 volt. So V is equal to 400 volt. The resistance of armature and shunt field are respectively, so armature resistance and shunt field resistance are 0.2 ohm and 100 ohm. Stray losses, so the another thing given is stray losses is equal to 1500 watt. Now calculate. So now it's time to write data to find. What data we need to find? So now it's time to look for data to find. We need to find, the first is mechanical efficiency. We will write this thing in short. First is mechanical efficiency, second is electrical efficiency, and the third is commercial efficiency. So these three unknown quantities we need to find: mechanical, electrical and commercial efficiency of this DC generator. So now let's head towards the solution. So whatever data is given to us, right? See, basically what do we need to find? We need to find mechanical efficiency, electrical efficiency and commercial efficiency, right? So let me briefly draw a diagram, right? A power stage of DC generator. So what this power stage represents: stage 1, stage 2 and stage 3. Let's call it as A, B and C. See, this thing is important to understand this thing, right? So A stage is the mechanical input. This is the mechanical input. Let me write it properly so that you can read. Mechanical input. Then over here, this mechanical input is converted into the electrical power at armature. So this is electrical power generated at armature, and this is electrical power delivered to load. So we can call this power as EIA. This is VIL, and this is mechanical input from the prime mover. So this is what the different power stages. Now what exactly happens, that when mechanical input power is given to this machine, there is some power loss, and that power loss is mechanical loss, which is a friction loss, and iron loss. So friction and iron loss occurs over here, and then we get EIA. When we get EIA, then the current starts flowing into the shunt and series windings of the armature and field. So then the Cu loss, copper loss occurs, right? So this is what the power stage is of generator. Now whatever thing we need to find, let me just put this thing in this manner, that first thing we need to find is mechanical efficiency. So basically what is mechanical efficiency as per our diagram, which is B by A. The second is electrical efficiency. So as per our diagram, the electrical efficiency is electrical output by electrical input. So it's C by B. And the third is its commercial efficiency. Basically commercial efficiency is all over or total efficiency of generator. So it is the final output C divided by total input A. So this is what we require to find, right? So now I think we all are clear with what exactly we want to find. To solve any example, see, every time you need to remember this, that to solve any example in any subject, you need to be very much clear that whatever data is given into example, this is first, and the second is whatever data you want to find. For both of these things you need to be very much clear. Once you are clear, half work is done. So now let's start to solve this example. So first of all we'll find the total output power, right? We'll go from C to A. So how can we calculate the total output power? So the total output power is V into IL. So do we have the terminal voltage? Yes, it's 400 and load current it's 80. So we have the value of terminal voltage and load current. So let me just calculate this thing. 400 multiplied by 80, it's 32,000 watt. So the output power is 32,000 watt, right? So this is the total output, which is equal to C, 32,000 watt. Now what do we need to find? Now we need to find B. And how we can find B? To find B, we need to find the copper losses. If we add copper losses in this power, we'll get total input power, right? See, we need to find this B, right? This is electrical input, and basically the input is output plus loss. Output we got over here, the losses, which is copper losses, occurs, right? So once we add these two terms, we'll get B. So now let's calculate the losses. And which losses we need to calculate? We need to calculate the copper losses. And which machine is this? A DC generator supplies load of 80 ampere and 400 volt, the resistance of armature and shunt field. So whatever the resistance is given to us, it is armature resistance and shunt field resistance. So from this we can say that our machine is a shunt generator, right? It's our armature, shunt winding and the load, right? So here we have RA, here we have RSH. So what is the copper losses in this, right? If we talk about shunt generator, then what is the equation for copper loss in shunt generator? The equation for this loss, copper loss, is equal to copper loss occurs in armature, IS square RA, plus copper loss occurs in shunt, ISH square RSH. So this will be the equation for copper losses. Now to find copper losses, do we have armature current? No, we don't have. Do we have the shunt field current? Even that also we do not have. So now what we will do, first we will find the shunt field current, and then we will find the armature current. From these two we will calculate copper loss, and from this copper loss we will calculate total input. So how we can calculate ISH, shunt field current, right? Let me use the equation for this shunt field current. Shunt field current is the current passing through this branch. And how we can calculate current passing through this resistance? Voltage across this resistance, VSH divided by RSH. And VSH at this 2 point, which gives us, which is equal to the terminal voltage V, which is given to us equal to 400 volt. So we can write the equation of ISH is equal to V by RSH, and V is equal to 400 volt divided by RSH, which is equal to 100 ohm. So I think we do not require calculator for this, right? It's 4 ampere. So the ISH we got, which is 4 ampere. Now we'll calculate IA, which is this current, right? Now to calculate IA, what do we require? We want to calculate IA. IA is divided into two sections, IL and ISH. So to calculate IA, our equation will be IA is equal to ISH plus IL. So do we have ISH? Yes, we do have found it just a few seconds before, right? And IL, which is given to us, it's 80 ampere. Okay, so our work is reduced, right? Be happy. This example is not going to be too long. So let's just place this value. IL is equal to 4 and ISH is equal to 80 amps. So IA is 84 ampere. So now we have the value of IA and ISH. RAIA is already given. So from this, if we calculate copper loss, IA square RA plus IH square RSH, then this will be IA is 84 into RA gives us 0.2 multiply by 0.2 plus ISH is 4 square and RSH is 100 multiply by 100. So 84 into 84, 7056 multiply by 0.2, 1411.2. So this gives us 1411.2, which is armature copper loss, and field copper loss is 4 square is 16 and 16 multiplied by 100 is equal to 1600. It's as simple as it looks like, right? 16 into 100. So it's just a minute, right? It's 16 multiplied by 100, so it's 1600. So if we add these two things, we'll get 3011.2. so our copper loss will be 3011.2 watt. So this is our copper loss. So we have got this copper loss. If we add this copper loss in the output, we'll get the electrical input, right? The second stage. So just add this thing over here and we'll get electrical input or into bracket EIA, which is equal to output, which is 32,000 watt plus 3011.2. So total 35,011.2. So this is our electrical input, which is B. Now if we add mechanical loss and iron loss into this input, we will get mechanical input. And see, whatever data given over here, stray loss comprises of iron loss plus mechanical loss. So the combination of these two loss is known as stray loss. So this loss is directly given to us, and it is 1500 watt, right? So now if we calculate mechanical input, which is electrical output, which is stage B. Electrical output for this is this. So electrical output plus stray loss. So what is electrical output? Electrical output is 35011.2 plus stray loss is 1500 watt, which gives us 1500 watt, which is equal to plus 1500 gives us 36,511.2. 36,511.2 watt. So now we have got A, B and C. So what is our mechanical efficiency? Mechanical efficiency is equal to B by A, right? So it's B by A. So whatever we have got here, 36,511.2 and B, which is 35,011.2. So the efficiency we get, let me calculate this thing, divided by 36511.2, which gives us 95.89. So it's 0.9589, and if we convert this efficiency into the percentage, then we'll get 95.89 percentage. So this is our mechanical efficiency, right? Now we'll go for next, which is electrical efficiency, which is C by B. Electrical efficiency is C by B. So C is our final electrical output, right? What is C? C is our final electrical output, which is 3200 watt. Sorry, not 3200, 32,000 watt. And the input for that is electrical input 35,011.2. So now let's just calculate this thing. 32000 divided by 35011.2 gives us 91.3, 0.9139, 0.9139. If we converted this in percentage efficiency, it gives us 91.39% efficiency. Now the commercial efficiency. Commercial efficiency is total output divided by total input, or we can write this commercial efficiency as total efficiency also. right? So commercial efficiency or total efficiency, they means one and the same thing. So our final output is 32,000 watt divided by our input A is 36,511.2. So now let's just calculate 32,000 divided by 36,511.2 gives us 0.8764. 0.8764, and if we convert it into percentage, we'll get 87.64%. So this is how we can calculate the efficiency, mechanical, electrical and commercial, or total efficiency, right? So just look at this example. If you have any doubt, then you can ask me in comment section. So we'll start with given data. So let's start understanding that whatever data is given to us, a 20 kilowatt 250 watt DC shunt generator. So first thing given to us is P is equal to 20 kilowatt. The next is voltage. V is equal to 250 volt. Then a DC shunt generator. So the type of generator is shunt generator. Has iron losses and mechanical losses of 800 watt and 750 watt. So the iron loss is equal to 800 watt and mechanical loss is equal to 750 watt. Resistance of armature and the shunt field winding are respectively, so RA and RSH is equal to 0.1 ohm and 125 ohm. Find the full load efficiency. So now we'll go for data to find. कौन सा डेटा हमको फाइंड करना है, which data we require to find, and that is full load efficiency. Full load efficiency. So this is what we require to find. So now let's start the example and we'll find full load efficiency. For that, let's go for solution. So the equation of efficiency is equal to output by input. So what data is given to us over here? The data is given to us is equal to power, voltage, shunt generator, iron loss, mechanical loss and resistance, right? So basically the output of the machine, the efficiency is comprises of output by input, and the output of machine is 20 kilowatt, which is given, input which is not given. So first we need to find the input. So let's just modify this equation. In order to find input, what we require to do, right? Input हमको जब find करना है तो हमको क्या करना पड़ेगा? So for input, the equation for input is input is equal to output plus losses. आउटपुट प्लस लॉसेस. आउटपुट प्लस लॉसेस में अभी हमारे पास यहाँ पर क्या है? हमारे पास आउटपुट तो है, लॉसेस में कौन कौन से लॉसेस दिए हुए हैं? आयन लॉस है हमारे पास, मैकेनिकल लॉस है. तो कौन कौन से लॉस होते हैं, अभी कौन कौन से लॉस बाकी है? विच आर द लॉस वी स्टिल रिक्वायर टू फाइंड? So we require to find copper loss, iron loss and mechanical loss. From these three we have iron loss and mechanical loss, so only one loss we require to find. So in losses we subdivide this category into Cu loss, iron loss and mechanical loss. So from this three, mechanical loss is given to us, iron loss is given to us, so we need to find this copper loss. So now if we talk about this copper loss is constructed of armature Cu loss plus filled Cu loss, and armature copper loss is given as Ia square Ra, and filled copper loss is given as ISH square RSH. So this is we require to find. Now let's check out that armature current is given. No, it's not given, and shunt field current is also not given. So what do we require to find? We require to find armature current and shunt field current. So let me draw the diagram first, right? The diagram for the shunt field winding shunt generator is like this, and it is the load. So the condition with us is like this: the load is of 20 kilowatt. What do we require to find? The first case we require to find ISH, and next we require to find IL. If we have these two currents, from that we can find Ia, and if we have Ia, from that we can calculate copper loss, from that we can calculate input, and from that we can calculate the efficiency. So this is the map of our example, that how we are going to solve this example, right? So let's work according to this map. So first we'll try to find ISH, shunt field current. So the shunt field current is voltage across this two terminal. So the voltage across this two terminal is V terminal voltage, and which is given to us as 250 volt, right? So ISH is equal to V divided by RSH. V 250 and RSH is 125. So it's very simple, it's 2 ampere, right? 125 250, so it gives us ISH is equal to 2 ampere. Now what do we require to find? Now we require to find Ia, and the equation for Ia is Ia is equal to ISH plus IL. We just have found ISH, right? Now we need to find IL, load current. So how do we calculate load current? We have the power. So from power we can write P is equal to VI. So I is equal to P by V. So it's 20,000 watt divided by 250 volt. So let's calculate this thing. Let me 20,000 divided by 250 gives us 80, right? So the amount of current IL is equal to 80 ampere. So now let's just write Ia. ISH is equal to 2 ampere, this is 80 ampere, so Ia will become 82 ampere. So this is our Ia, we have found Ia, we have found RSH. So let's place this two quantity over here and find the total copper loss. So the equation for copper loss, Cu loss is equal to IS square RA plus ISH square RSH IA, it's 82 amp square of 82, and RA is 0.1 plus ISH is equal to 2 ampere and RSH is 125. So now let's calculate this thing. 82 into 82 multiply by 0.1 gives us 672.4. 672.4 plus 2 into 2 4 multiply by 125, it gives us 500, and 500 plus 672.4 plus 672.4, 1172.4. so it's 500, and the total of this two is 1172.4. so CU loss is this, right? Now what do we require to do? We have found copper loss. So from this, if we add all these three quantity, copper loss, iron loss and mechanical loss, we will get input. We get losses, right? This is to find losses. So total loss, let's just quickly mention over here. Total loss is equal to copper loss 1172.4 plus iron loss is 800 and mechanical loss is 750. So 800 plus 750, which gives us plus 800 plus 750, 2722.4. 2722.4 watt. So this is the total loss of machine. Now input is equal to output plus loss. This is total loss. So the output we get, output is given 20,000 kilowatt. So 20,000 watt, and loss is 2722.4. so let's just add these two and we'll get 22,722.4. 22,722.4 watt. So this is our input. Now let's go and calculate the efficiency. So the efficiency is output by input. Output is 20,000 watt and the input is 22,722.4. 22,722.4 watt. Let's just calculate. Which gives us 88.01. 88 point, we'll write this 8801, and if we convert this into the percentage efficiency, it will give us 88.01%, right? So this is 88.01%. So this is example number 2. The next example is, so let's just quickly start to solve this example. So we'll take green pen and start writing given data. So whatever data is given, we'll write constant loss. Constant loss is given to us. Constant loss of 250 volt DC generator are 1250 watt. So constant loss is 1250 watt, which gives the terminal voltage V 250 volt. Find the current corresponding to maximum efficiency. So it's now directly given what data we need to find, right? Data to find. And what do we need to find? Current corresponding to maximum efficiency. IA for maximum efficiency, that we need to find. Current corresponding to maximum efficiency. Also find output power for maximum efficiency. So we need to find P out, the same at maximum efficiency. Resistance of armature is 0.1 ohm. So the armature resistance is given RA, it's 0.1 ohm. So this is what we have, right? And what do we need to find? We need to find current at maximum efficiency and power at maximum efficiency, right? So first of all, to solve this thing, let's write the equation for maximum efficiency, right? So that we'll have the idea that how we can solve this example, right? Initially we do not know how we approach to solve this example. So what we'll do, we'll just write the equation for maximum efficiency, and then we try to relate that any of the quantity just appears in that or not, right? So now we have maximum efficiency equation, and the equation for maximum efficiency is IA square RA is equal to WC, or the same thing we can write as variable loss of machine is equal to constant loss of machine. So this is the equation for maximum efficiency. Now look at here, IA, armature current, appears into the equation of maximum efficiency, and we just need to find that only, right? So this is constant losses, which is directly given to us. RA is armature resistance. So everything we have, we just need to rearrange this thing and solve it mathematically, right? So let's just rewrite this thing. It's WC by RA. And if we want to convert this thing into IA, then IA is equal to under root WC by RA, which gives us constant loss of 1250 divided by 0.1. 1250 divided by 0.1 gives us 12,500, right? And the under root of this is 111.8. So IA is 111.80. 111.80. So we have found IA, and it's easier than what I thought. How we will solve this example, it's a little bit easier than what I thought, right? So this is the armature current we have. Now what do we need to find? Now we need to find the output power, right? Output power. But we need to find output power at maximum efficiency, right? Output power at maximum efficiency. So first simply write what is the equation of output power, right? See, this is the trick to solve any of the example. If we know how to solve, or if we do not know how to solve, just write the equations and then we will find the way to solve the example. So the equation for output power, P out, is equal to V into IL, right? There are others equation also, that input power plus input power minus losses, right? The output power is equal to input power minus power losses. This is the another equation. So see, uh, as per the data we are having, right, the data we are having, from that data which equation to use is the most appropriate, that equation we need to use to solve our examples. See, over here we have terminal voltage. Is it given to us? No, the terminal voltage is not given to us. Is line voltage is given to us? Line voltage is also not given to us. So it's tough to find line voltage, right? Just a minute. Yes, terminal voltage is given to us, but line voltage is not given. So if we are able to find line voltage, we will get the output power and it will become very easy, right? Now let me tell you that to find IL we require the load resistance or the total output power, but that we need to find. So anyway we cannot find directly load current without assuming some data. So what we will do over here, we will assume that IA, armature current, is almost equal to IL, because we have solved many previous examples, right? And in that previous examples also we have seen that armature current is almost equal to the load current, and we have just found over here the armature current. So what we will do, we will take this armature current almost equal to the load current and try to solve the P output. So now if we solve the P output, then voltage is 250 volt multiplied by IL, which is 111.80, right? 111.80, and that gives us the answer. 111.80 multiplied by 250, 27950.84, 27950.84, which is our P output, right? And why this is our P output at maximum efficiency? Because we have taken armature current at maximum efficiency, so this is output power at maximum efficiency, right? So this is what the thing is. If you really want to find that what is the maximum efficiency for this machine, right? If this is just a shake of understanding, right? If we want to find what is exactly the maximum efficiency of this machine, how we can calculate the efficiency? Output by input, right? And input is, the equation can be modified as output plus losses. What are the losses? Copper loss, iron loss, and mechanical loss. Copper loss is variable loss, mechanical loss and friction loss is constant loss. So if we rewrite this equation as output divided by output plus constant loss plus variable loss, right? So constant loss plus variable loss, we have the output power is 27950.84 divided by output 27950.84 plus constant loss is 1250 plus variable loss. We do not have variable loss, but see, what is the condition for maximum efficiency? Variable loss is equal to constant loss. So we will just place variable loss equal to constant loss and just sum up everything. 1250 plus 1250 plus the output power is 27950.84 gives us 30450.84, right? 30450.84, and let's just divide this with the input 27950.84 divided by 30450.84, which gives us 91.79, right? which gives us 91.79. 91.79 percentage will be the maximum efficiency of this machine. इस मशीन की ये मैक्सिमम एफिशिएंसी होगी. So now if anybody wants to ask any question, any doubt, then you can write in comment section. This is the end of the video.